Okay, section 1.5 deals with elementary matrices and finding the inverse of a matrix. Now, in the previous lesson, when we started talking about inverses, we saw that for a matrix B to be the inverse of a matrix A, we needed two things to hold. We needed the product of A with B to be the identity, and we needed the product of B with A to be the identity. And then once both those properties are satisfied, we say that A is invertible, and B is the inverse of A, and A is the inverse of B. Now, in the previous sections, we set up these long, cumbersome equations, and we solved for the matrix B in that way. Now, that is a very inefficient way of calculating an inverse, so we want to find more efficient ways of doing so, and that certainly isn't. So that brings us to elementary matrices, and elementary matrices are going to help us to find inverses of matrices. So just recall the following three elementary row operations. The first operation we talked about is you multiply one row through by a scalar C, or you could interchange two rows. That's the notation we use. Or you can change a row by adding one multiple of another row to the row that we're changing. And we always write the row that we're changing first. So in this case, you're writing the ith row, changing the ith row, and you're writing that first, and you're adding a scalar multiple of the jth row to the ith row. Okay, so we say that the matrices A and B are row equivalent if you can obtain the matrix B from the matrix A by taking the matrix A and applying a sequence of elementary row operations to the matrix A, and that will eventually lead to the matrix B. If that's the case, we say they are row equivalent. Okay, so again, you can apply the reverse on B to go from B to A. So this is in this case, this example here, we're moving from the matrix A to the matrix D by taking A and first changing one of its rows by adding a multiple of the jth row of A to the ith row of A, and that brings us to a matrix B, and then taking B and interchanging two rows, the ith row and the jth row of B, to get to C, and then we change C by multiplying a row of C with a scalar C, and then we get to the matrix D. Now I can do the reverse to D and go from D to C, and then go from C to B, and then go from B back to A. Alright, this brings us to the definition of an elementary matrix. An elementary matrix is a square matrix, and it's a very simple matrix in the sense that you can construct it using the identity matrix I subscript n. And what you do is you take the identity matrix In, and what you do is you apply one single elementary row operation to the identity matrix, and the end result there will be an elementary matrix. So you apply either this operation or that operation or that operation, and very importantly, you only apply it once. You only apply it once, exactly once. Okay, now looking at the matrix E1, I constructed E1 from the identity matrix by simply doing the following. So taking the identity matrix there, what I've done is I have interchanged the first with the third row. So that's what I've basically done, and that will give me E1. Then going back to the identity matrix, looking at E2, I can get E2 from the identity matrix by multiplying the second row of the identity matrix, which is that row there, with 8. And so I get E2. Okay, and then how do I get E3? Going back to the identity matrix. Okay, how do we construct E3? So again, what we're doing is we take the second row of the identity matrix. So there's the second row, okay. There's the second row, and what I'm going to do is I'm going to multiply the second row with -4. Okay, so then I get basically -4 there. Okay. And what I'm going to do is I'm going to take the third row of I, and I'm going to change it. So that is the third row of I. And I'm going to change it by taking a constructing a new third row that I'm going to form by adding -4 times the second row to it. Okay, so I'm essentially adding R3 and -4 R2, and that is going to provide me with a new row, which is going to be the row 0, -4, 1. Okay, so I'm basically now changing the identity matrix to E3 by doing that operation. So I'm taking it and I'm replacing. Okay, so how I got there was I applied this operation here. Okay, in the next example, let's the aim of the next example is to illustrate the theorem that comes after it. If we look at E, the elementary E is clearly an elementary matrix. We obtained it from the identity matrix by switching the second and the third row of the 3 by 3 identity matrix. Now, if we multiply it with A, you can go it's the 3 by 3 times the 3 by 2, so it's going to be that 3 by 2 EA. And if we look at the difference between A and EA, we see that the first row of A is exactly the same as the first row of E times A. However, if we look at the other two rows, if we look at the row, the second row of A, and we look at the third row of A, then when we inspect EA, we see basically that the second row of A has now become the third row of EA, and the third row of A has now become the second row of EA. So basically, these two rows have basically interchanged, moving from A to EA. Okay, now that's pretty interesting, because what is the connection in this case to E? How did we get to E from the identity matrix? How did we get to E from the identity matrix? So taking the identity matrix, we basically did what? We interchanged the third and the second row, and in doing so, we've constructed the elementary matrix. We've constructed the elementary matrix E. Okay, so we did that by, again, we interchanged the second row with the third row from the identity matrix. Now, if we take A and we calculate the product EA, then I get it from A by just applying the same rule to A. So all I do is I interchange the second row of A with the third row of A, and I get EA. Okay, but that could just be coincidence. So maybe that's the connection with that particular example. Maybe it's just good for us to look at the next example and see if this rule still applies. Maybe we can find a generalization. Okay, let's look at the next product. So this E is clearly an elementary matrix. Okay, let's take the identity matrix and we can construct E by doing the following. We take the last row of the identity matrix, okay, and we use that as our last row. We take the second last row of the identity matrix and we use that row as well. Okay, and then what we do is we are going to form the first row of our elementary matrix by taking the first row of the identity matrix and then taking the third row of the identity matrix Okay, that's the third row of the identity matrix. And I'm going to multiply it with 2. And then I'm going to add those 2 rows. And what am I essentially going to get is 1, 0, 2. Okay. And that is going to be my new row. Okay, so that is going to be my elementary matrix. Okay, so again we got E by taking the identity matrix and changing the first row by adding twice the third row to it. Now let's look at A and let's look at EA. Now comparing the two, we see that the last row of A is exactly the same as the last row of EA. The second row of A is exactly the same as the second row of EA. Now we see only the first row has changed going from A to EA. Now if we look at this change, what exactly is this change? Well, if we take the third row of A, okay, if we take if we take A and we change A as follows, we take the first row of A, we're changing it by adding twice the third row of A to it. So what then does that become? It becomes a new matrix, right? So we're taking 0 and 5, minus 3 and 0, and 1 and 2, and we're doing the following. We're taking that row there with 2, so we get 0, 10, and then what we're going to do is we're going to add that to the first row of A, and the first row of A we said is the row 1, 2. Okay, so basically you're going to add that and you're going to basically get 1, and you're going to get 12. Okay, and so replacing the first row of A with that modified row, we get the product of E with A. So we obtained the product of E with A by modifying A, and we modified A by using the operation that we used to get the elementary matrix E from the identity matrix. We used that very same operation and we applied it to A, and we constructed the product between E and A. So now the question is, can this we had these two examples where the operation used to find the elementary matrix happened to be the operation that we could apply to the matrix A to get the product of with the elementary matrix. So now the question is, can you go and generalize this argument? Is it in general true that if you use that particular operation that you use to get the elementary matrix from the identity matrix, if you use that on the matrix A, does it give you the product? Okay, so that brings us to this theorem. So Theorem One states that let A be an arbitrary n by n matrix. Then it says if the elementary matrix E results from performing a certain row operation on IM, then EA is the matrix that results when the same operation is performed on A. Okay, let's look at the M by M identity matrix. The blue is the ith row and the yellow is the jth row. Okay, and what I'm going to do is I'm going to construct an elementary matrix from this identity matrix. And how am I going to do it is I'm going to interchange the ith row of the identity matrix with the jth row. So what I'm going to do is I'm going to take the ith row of the this identity matrix and I'm going to interchange it with the jth row. So I'm going to move the jth row and I'm going to move it into the position of where the ith row used to be. Okay, like that, and then I'm going to move the ith row in the position of the jth row. So there I've interchanged the two rows. And now just take note of those positions that the ones moved to. Okay, so again, that's the jth row and the ith row of the original matrix. Okay, and again there we've got those values that interchanged there. And that we're going to call that is what we're going to call this elementary matrix. So let's take the product of this elementary matrix with A. Okay, so taking E as product with A, we get, okay, there we've got our matrix there, and multiplying that with A. Okay, there we've got our product and working that out. So we know how to do that. We're going to dot this row with that column, the column being the first column, right? And then you're going to move it, you're going to get the basically the first row by moving through all the columns and dotting that with the first row of E. And moving on up until the last column, you generate the first row of the matrix A. Right, then you're going to move on to the second row of E that you're going to dot with all the subsequent columns of A. And moving on to the second row, you're going to generate the dot products are all going to generate the second row of A. Okay, and then you're going to carry on straight up until you get to the ith row of E. Now the ith row of E has a 1 in the jth position. So the 1 in the jth position you're gonna firstly dot that red row with all the columns, subsequent columns of A, and that one encircled in green, like I said, lies in the jth position of the ith row. So that one is going to correspond to the position of the jth row, and so you're going to generate all the jth row elements. All right, so you're going to generate the jth row in that position. Then moving on, you're going to carry on until you get to the jth row of E, and it's got a 1 in the ith column. So again, if you dot this row with all the columns, you're going to start with the first column and move to the nth column. You are pretty much going to generate the ith row of A in this jth, as the jth row of the product between E and A. So there's going to be your jth row, and it's going to be the ith row of A. Then you're going to move on until you get to the very end. And so dotting the last row of E with all the subsequent columns of A, we generate the last row of the product between E and A. And that's going to be the last row of A. Okay, so now let's quickly look at this product matrix. How did we get this product? Well, we took the matrix A, and all we did is we interchanged the ith row of A with the jth row of A, and that resulting matrix is in fact the product between E and A. So there we see in the ith row we've got the jth row of A, and in the jth row we've got the ith row of A. Now, how did we get, if we look at so essentially what we did was we constructed the product between E and A by simply taking the operation that we used to get the elementary matrix. We applied that same operation to A to get the product between E and A. Okay, let's look at the identity matrix again. And what I'm going to do is I'm going to focus on the ith row of the identity matrix again. And now I'm going to look at my second type of operation, which is multiplying the ith row of the identity matrix with a scalar C. And in so doing, I'm going to create the elementary matrix. Okay, and please take note that the 1 in the ith row obviously lies in the ith column as well. It's the entry in the ith row and the ith column. Okay, so that entry I'm going to multiply with C and then get my elementary matrix. Okay, so replacing the 1 with a C, I get my elementary matrix. Now, let's go and see what happens if I multiply this matrix E with the specified matrix A. Okay, so writing down the two matrices there, we get E times A. And now it's just a straightforward multiplication that you're going to work out. So taking the first row of E and then dotting it with all the subsequent columns of A, and then running through all my rows of E, we will get the product between E and A. Right, so there, dotting the first row with the first column, and then running through all my columns, I'm basically going to get the first row of A. Right, then running through moving on to my second row, if I take the second row and I dot that with the all the subsequent columns of A, I'm going to generate the second row of A as my second row of my product. Okay, there we get that. And then we continue in this fashion until we get to the ith row of E, and multiplying this with or dotting it with all the subsequent columns to generate the ith row of the product. And that's basically going to be pretty much, it's going to be the ith row of A that I can go and take, but with one difference. I have to multiply each entry of the ith row of A with the scalar C. Okay, so there I've generated my ith row, and then again I have to continue this process through right until the last row of E, and then going through the subsequent columns I'm going to generate the last row of A as my last row of the product. Okay, so there we have our last row. Okay, so what can we say now? That the product of these two matrices could have been determined basically by just taking the operation that I used to get the elementary matrix from the identity matrix and just simply applying it to the matrix A. You'll see that if I take A and I multiply the ith row with C, that was exactly the same operation that I used to get the elementary matrix E. So I took the ith row of the identity matrix and I multiplied it with C, and then to get the product between E and A, it is just pretty much exactly the same as taking A and just applying that same operation to A. Okay, so that was the second operation. Let's look at the last operation. Okay, so the last operation involved taking a multiple of one row and adding it to the other. So I'm going to take the identity matrix and I'm going to look at the ith row and the jth row. I'm going to take a multiple of the jth row and I'm going to add it to the ith row. And in doing so, I'm going to change the identity matrix into an elementary matrix. Now just take note that that 1 lies in the ith column and the ith row of I, and the one in the blue row, which is the jth row, that lies in the jth row and the jth column. Okay, so now doing that modification, we get we have to consider now the matrix separately. And again, we're going to take the jth row of I, and we are going to multiply it with, we're going to take that row separately, and we're going to multiply it with a scalar k, and then meaning that we're going to replace the 1 in that blue row with a scalar k, like so. Okay, and then we're going to add it to the ith row. Doing that, you'll see that the scalar k lines up with a 1 in the blue row, but it lines up with a 0 in the yellow row. Okay, so adding that, we're going to have in the jth column of the ith row, we're going to have a new entry which is going to be k. And also note that the blue row has a 0 in the ith column, so adding that up, it's not going to affect the 1 in the ith column of the ith row. And again, take note that the entry k now lies in the ith row and the jth column. And it's just important for us to note that, because when it becomes relevant when we calculate the product of E with A. Okay, so the only thing that changed here is the ith row of the identity matrix. It gained an extra entry, a k, in the ith row and the jth column. Right, so now we can go and calculate the product. So taking the matrix E and multiplying that with the matrix A, we then see what the end result is. Okay, so taking the matrix E and then taking that, writing it next to the matrix A, we get the product, and now we can go and see what this, what the effect of the operation is on the matrix A. So again, you take the first row and you dot it with every single column to generate your first row of my product, and that is pretty much just going to be the first row of my matrix A. Then moving on to the second row, we're going to take the second row of E and we're going to dot that through with every column of A. And in so doing, we're going to generate the second row of the matrix A. Okay, doing that, we get the second row of the matrix of the product. And then what we're going to do is we're going to carry this process through until we get to the ith row of E. And we're going to take the ith row of E and we're going to dot that with the with every subsequent column of A. Now if we look at that 1, where's that 1? That 1 has a position which lies in the ith row and the ith column of the matrix E. So what's going to happen is if I'm going to dot that through with all the columns, that 1 is going to line up with the ith row of A. So I'm basically going to generate the ith row of A in my ith row of my product. But not only that, I'm going to generate some extra terms as well, because I have to take the value k into account. So the k, we said, was in the ith row and the jth column. Okay, so that's in the ith row and the jth column. So if I dot that with every one of the columns of A, we see that that k lines up with the jth row of A. So because it's a dot product, I have to add the entries. So I'm going to take the jth row of A and I'm going to write it separately, and I'm going to multiply it with a scalar k individually, and then I'm going to add that to the ith row of A. Okay, so there I've got my scalar entries, and then I'm going to add them to the respective column entries of the ith row of A. Okay, so just spacing it out a bit and writing those terms next to the ith row entries. I just have to add them up because remember it's a dot product. So adding it up, I get the ith row of my product matrix. Okay, and like I did before, I have to carry this process through until I get to the last row. And I have to then dot the last row of E with all the columns of A. And in so doing, I'm going to generate the last row of my product, which in this case is going to be the last row of A. Okay, so doing that, we have then our final product. So look at how we obtained the product between E and A. What I did was I took the matrix A, I took the jth row and multiplied it with a scalar k, and then I added it to the ith row to generate my product EA. Now this happens to be, that operation I used on A happens to be exactly the same operation that I used to get E from the identity matrix. I took the identity matrix, took a scalar multiple of the jth row and added it to the ith row. And in this case, the product I got is exactly the same operation I applied to A. So this clearly shows that that the theorem of the product of an elementary matrix with a normal matrix or just any arbitrary matrix is pretty much just applying the operation I used to get E onto my matrix A, and that will give me the end product. Okay, now this is important, as you'll see later, because elementary matrices play an important part in inverting general matrices. Okay, let's look at the inverses of elementary matrices. Now it happens that you can calculate the inverse of an elementary matrix very easily. Let's look at the first example. The first example is an elementary matrix that we obtained from the identity matrix by switching the second and the third rows around. Now, the question now is, what is the inverse of this particular elementary matrix? So how do we determine the inverse of a matrix? Now recall that the inverse of the matrix E is a matrix A such that A times E is the identity matrix. And not only that, the product in the reverse order also has to hold, and it has to also be the exact same thing, which is the identity. Now when that happens, we say that A is E's inverse and E is A's inverse. We know this from section 1.4. So now what we want to do is we want to go and work out what this matrix A must be. Now they've already given you the answer there, but let's see why that is the case. We are going to apply our product rule for elementary matrices. We know from the previous theorem that we know how to calculate the product of an elementary matrix with another matrix. So that is what we're going to do now. So what do we need A to look like? Okay, so this is a straightforward procedure. So what I'm going to do is I'm going to take I'm going to take the necessary requirement, which is the identity matrix, and I'm going to take E, and then I'm going to ask myself, what do I need to make the matrix A such that I get that the product of E and A is the identity matrix. Okay, now the question is, how did I get E? I got E by switching the second and the third row of the identity matrix. Now what I'm going to do is I'm going to take E and I'm going to take its duplicate and I'm going to make that my hypothetical matrix A. Now let's see if we have equality on the left and the right hand side. So let's make that my matrix A, and we have E on the left hand side. Now what is my product rule? What does it say? It says that basically I can calculate the product of E and A by simply applying the operation that I used to get from my identity matrix to E, by simply applying that operation to A. Now how did I get E? I switched the second and the third row of the identity matrix. Okay, so apply that very same operation to A. So go to A and switch the second row of A with the third row of A. So what happens if we switch those two rows what happens if we switch them around? So you're going to take the last row of A and you're going to switch that with the second row of A. Okay, so what do we get in the end? We get the identity matrix. Okay, so it seems that this is working from if we multiply E on the left hand side. Now just observe that A happens to be equal to E. Okay, so A is pretty much E. Now let's take A and write A on the left and then write E on the right, and then see if we get the identity as well. Well, it is going to be the same. How did we get A? We got it from the identity matrix by switching the second and the third row around. So the product rule says that whatever I did to get the first elementary matrix in my product, I just have to apply that to the matrix that occurs second in the product, which in this case is E. So let's just do that operation. How did we get E1? We switch the second and the third row. So apply that to E. So switch the second and the third row of E around, and what are you going to get? You're going to get, just like you had in the previous case, you're going to take the matrix E and you're going to switch the second and the third row around. Okay, so there we take the third row and we move the second row into the position of the third row, and there we have the second row. Okay, so that's the identity. So it's clear that the inverse of E is A, and the inverse of A is E. So they are both one another's inverse. So E is its own inverse. Okay, now let's look at the second example. Let's quickly look at the second example. The second example is another elementary matrix. And how did we get this elementary matrix? We took the identity matrix and we multiplied the second row with a scalar C. Now the question is, what is the inverse of this matrix E? So what do I have to multiply with E to get the identity matrix on both the left and the right hand side? What do I have to multiply E with? So let's take E, and what I'm going to do is I'm going to change, I'm going to ask that question. I'm going to ask the question of what must I make A to get the identity matrix on the right hand side. So I need to choose A in a very particular way. Now I know that the product of E with A can be determined by applying the operation I use to get E from the identity matrix to A. So when I apply this operation to A, the end result has to be that identity matrix on the right hand side. So what do I need to choose A as? Well, I'm going to choose A as E that I'm going to modify slightly. I'm going to take E and I'm going to write the scalar entry in the second row. I'm going to write that as 1 over C as opposed to C. And setting A up in this way, let's see if that actually gives me the identity on the right hand side. Okay, so there's E. Okay, and now let's multiply E with A. Now what was the operation we used to get E? I multiplied the middle row with a scalar C. So apply that same rule to A. I'm going to multiply the middle row of A with C. And so the C is going to cancel with the 1 over C, and it's going to lead to a 1 on the matrix on the right hand side. So that is clearly going to give me the identity matrix. So now note that A is itself an elementary matrix. And how did we get to A? We took the identity matrix and we multiplied the second row with a scalar, and the scalar in this case was 1 over C. So now again, how do we multiply this matrix A with E? We apply whatever the operation is that we use to get A from the identity matrix. We apply it to E in this case. So what did we do to get A? We multiplied the second row with 1 over C. And so the C will cancel with the 1 over C. and on the right hand side we will get pretty much the identity matrix. Okay, so there's the identity matrix on the right hand side. So it's a repeated application of the product theorem that we did basically the proof of previously. Okay, so perhaps let's just look at the last example. So we've got the elementary matrix there, E, and how did we get to E? We took the identity matrix and we added the multiple of the last row, K, to the second row. So now to get the A, which is E's inverse, we ask ourselves, what does A need to be so that if I multiply E with A, I get the identity on the right hand side. So I need to choose A in a very particular way. How did we get E? We applied that adding the multiple of the last row, the identity matrix, to the second row. So now I need to apply the same operation to A to work out the product. So what do I need to choose A to be so that I get the identity on the right hand side? Well, what I'm going to do is I'm going to pick A to be pretty much the matrix E, but I'm going to make the entry in the last column of the second row, the K entry, I'm going to make that a negative. Now let's see if I choose A to be that way, how it will look like on the right hand side in terms of the identity. Okay, so picking A there, we get 1, 0, 0, 0, 1, and I'm going to make that a minus K. And the last row stays the same. So, applying my product rule, I have to apply exactly the same operation I used to get E from the identity matrix to the matrix A. So let's apply that operation to the matrix A. So I'm going to apply the same operation to matrix A, and that is, I'm going to take the last row of A, multiply it with K, and add it to the second row of A. And so the last row becomes 0, 0, K, and we're going to add that to 0, 1 minus K. And the second row is then going to be modified, and it's going to become 0, 1 minus, well, it's going to become 0, 1 minus K plus K, which is 0, 1, 0. Right, so again, we get the identity on the right-hand side. Okay, so again, the middle row becomes that, and then the last row stays the same. So we've gotten the identity by multiplying E with A. Now the question is, what is A times E? Is it still the identity? Well, note that the chosen matrix A is itself, it is an elementary matrix. A is an elementary matrix. And what did I get to obtain A? I took the identity matrix, took the third row, multiplied with minus K, and I added it to the second row. So A is definitely an elementary matrix. Now, if I multiply A with E, the product rule just says, apply the same operation I used to get A from the identity, just apply the same operation to E. So we're going to do the same to E, so take the last row of E, multiply it with minus K, and then add it to the second row of E to generate the second row of the product of A and E. So you're going to have the product is going to have the same first row as E. It's going to have the same last row as E. The only difference is the middle row is going to change from 0, 1, K to 0, 1, 0, which is the identity. Okay, so basically Theorem 2, those three examples illustrate Theorem 2. That is that each elementary matrix is invertible. Okay, we know when you have interchanging two rows, the elementary matrix stays the same, or the inverse of the elementary matrix is pretty much the same as the elementary matrix itself. And then whenever you multiply, whenever you get an elementary matrix that you multiply one row through by a scalar, the inverse of that matrix is just going to be the same one, but you're going to just invert the scalar that you're multiplying through with. And then lastly, if you take one row and a multiple of one row and add it to the other, you're just going to, the inverse of that is just going to be the negative part of the scalar multiple, which is that part there. Okay, so each elementary matrix is definitely invertible, and the inverse is an elementary matrix of the same type. That's pretty easy to see that. Right, so E1, what is the inverse of E1 going to be? So we got to E1 by switching the first row and the third row of the identity matrix. So basically the inverse of E1 is pretty much going to be the same matrix, because if you multiply E1, let's call this matrix A. If you multiply E1 with A, whatever you did to get E1, you have to apply to A, and we switch the first and the third row of A of the identity matrix to get E1. So we're going to do the same to A. So we're going to pretty much take A and we're going to pretty much switch the first and the second row around, or the first and the last row around like that, and we're going to get the identity matrix. Okay, and again, if you multiply the two the other way around as well, where you write the first in the product, it's going to be the same story. A is also an elementary matrix. We got A by taking the identity matrix and switching the first and the third row. So whatever we did to get A, we do to E1, switching the first and the third row of E1 around. That is going to generate the identity matrix. So it's clear that the inverse of E1 is its own inverse. Okay. So let's look at the second one, E2. E2's inverse is pretty much going to be the matrix 1, 0, 0, 0, 1 over 8, 0, and 0, 0, 1. By the same rule, if we multiply A with E, with E2, whatever we did, if we multiply E2 with A, whatever we did to get E2 from the identity matrix, when I multiply E2 with A, I just apply that same operation to A, and in that case I'm going to just multiply the middle row of A with 8, and that's going to give me the identity matrix. And then turning it around, multiplying A with E2, how did we get A? We got A from taking the middle row of the identity matrix and multiplying through by a scalar 1 over 8. So multiplying A with E2, I have to do the same that I got to do. Well, I have to do the same operation that I used to get A from the identity matrix. I have to apply that to E2, and that's going to give me the matrix, the identity matrix. Okay, and then the last one, E3. The inverse of E3 is going to be the same story. It is going to be the matrix 1, 0, 0, 0, 1, 0, 0, 4, 1. Okay, multiplying E3 with A, I'm going to apply the exact same operation I used to get E3, which is taking the last row of the identity matrix, well, taking the second row of the identity matrix, multiplying it by -4 and adding it to the third row. So apply it to A, take the second row and multiply it with -4, and add that to the last row. The -4 is going to cancel with a 4, and we have the identity matrix. And then apply the same rule again, where we multiply A with E3 first. And how did we get A? We took the identity matrix, we multiplied the second row with 4, and we added it to the third row. So to get the third row, so whatever I did to get A, I have to do to E3. So multiply the second row of E3 with 4 and add it to the third row, and then that entry gets cancelled and we get the identity matrix. Right, so it's easy to invert elementary matrices. Okay, next up we've got inverses of row operations. Take a matrix and apply the scalar multiple operation to the ith row. You multiply the ith row with a scalar c. How do you reverse that operation? Taking the new matrix and multiplying through by a scalar 1 over c to cancel. Then if you take the matrix and you interchange the ith row and the jth row, how do you, to get a new matrix, how do you reverse that? Taking the ith row and interchanging it with the jth row of the new matrix around, and you get the original matrix back. Then the last operation, take k times the jth row and add it to the ith row. How do you reverse this operation? Take the new matrix, multiply the jth row of the new matrix with minus k, and add it to the ith row of the new matrix, and so those will change will cancel out, and you'll be left with the original matrix